Reminder, just in a nutshell, we've done all this as a reminder. Symmetric about the y-axis. Even functions. Even functions have reflectional symmetry across the y-axis. For an even function, or for a function to be even, that means that all f of negative x is equal to all f of x. That was the test that we gave. Okay, you take and you plug in negative x's for all of your x's, and if you end up with the same function you started with, then that's going to be an even function. It's symmetrical across the y-axis. An odd function was symmetrical about the origin. It had rotational symmetry about the origin. And the test for an odd function was f of negative x is equal to negative f of x. And then we had one other type of symmetry. All parabolas are symmetric across a line x equals negative b over 2a. So if you're dealing with, which by the way, number 3 and 1 kind of go hand in hand, right? Because some parabolas are even functions if you're missing your middle term. Now, if you throw in that 3x or 7x or 5, now it's not an even function. Now it's not going to be even nor odd. But if you don't have that middle term, pretty much if your b is 0, think of it like that. If your b is 0, look, x equals 0 would be your axis of symmetry. Well, is that not the y-axis? So those go hand in hand. So here we go, moving along. Discuss the symmetry of each graph, or of the graph of each polynomial function. 5x to the third minus x, you already know. I showed you the shortcut. This is going to be what kind? Odd. This is an odd function. It's going to have some symmetry about the origin. Just a reminder, though, to test to see what you do, you find f of negative x, which means take and plug in negative x for all your x's. Plug in negative x here, negative x to the third power. Does it remain negative, or would it be positive? Stays negative, right? So I'm going to put my negative out front. Negative 5x to the third. If you do negative, negative, that'd be plus x. And then you find negative f of x, which, by the way, we already know it's not even because this and this are not the same thing. But to test if it's an odd function, also find negative f of x, which pretty much means go through and find the opposite of all the terms here. Negative 5x to the third and plus x. Since these are the same, that would be odd function. It has rotational symmetry. We already know. Even function. All the exponents are even numbers, so therefore you're going to have an even function. To test it, find g of negative x, which means go in and plug in negative x. When you plug in negative x and you raise to the fourth power, does it make it negative, or does it stay negative, or make it positive? Good. So it stays 2x to the fourth. It's still positive. Autumn, what about when you plug in negative x here? Is it going to be positive or negative? Ignore this. I mean 3x squared. Will it be positive or negative? Positive. So you stay negative 3x squared. You don't have to go any further. You can, but you know if it's even, it's not going to be odd. Negative g of x would be negative 2x to the fourth and plus 3x squared. Since g of x and g of negative x are the same thing, then it's an even function. It would have symmetry across the y-axis. And this should be in your notes somewhere. Before we even start, Austin, is this going to be even or odd? Neither. It's not even, it's not odd, but it is a parabola. So it does have symmetry. Anytime you're dealing with a parabola, to find symmetry, you have a line of symmetry. We'll call it the axis of symmetry. This parabola will be symmetrical across the line x equals negative b over 2a. Seth, plug this stuff in for me. What's negative b? And what's 2 times a? X equals negative 3 halves. Don't just put 3 halves, but x equals 3 halves is going to be your line of symmetry. That's your axis of symmetry. This is also review behavior at an x-intercept. What I mean by behavior is when does it cross the x-axis? When is it tangent to the x-axis? And a reminder, here's your problem. In this function, if we're looking for x-intercepts, once again, we plug in 0 for y, and we solve it. Canada, what's our zeros here? What can I plug in here? Or what's my x-intercept here? Set it equal to 0, solve it, move the minus 1 over, you get good 1. And same thing here, x minus 3 equals 0. My 0 here is 3. But look at our powers. If you actually wrote this out, this function is actually x minus 1 times x minus 1 times x minus 3. So 1 is actually a root twice. It has a multiplicity of 2. So let's just talk about the nature of these two intercepts. Since 1 is a root twice, what is your function going to do at 1? It touches. Since 3 is a root 1 once, what is it going to do there? Cross. If your 0 is a root an even number of times, it touches. If it's a root an odd number of times, it crosses. Okay, that's what I mean by nature of the x-intercepts. Let's do this one. X to the third plus 2x squared minus 3x. Again, one of the hardest ones to factor. Everybody's looking, but there's no number out there. We like it when there's no number out there because if there's no number, that means that everything has an x. So the first step, factor out an x. You're left with x squared plus 2x minus 3. Jason, help me factor that. Multiplies give you 3. 3 and negative 1, right? So I have 3 zeros. My 3 zeros are 0, negative 3, and positive 1. 0, negative 3, positive 1. There is absolutely no multiplicity on those. They're all roots once. Since they're all roots once, then it says find the x-intercepts to determine whether the graph crosses or touches at each. All 3 of these would cross. That makes sense. Okay, next up, talking about what graphs look like, polynomial graphs, and some of you might have already caught on to this. X squared, and any type of x squared graph will always look like a parabola. And all of these, notice these are all my even degrees. Even powers, second power, fourth degree, sixth, no, actually negative and negative. But sixth degree, it follows the same suit. If you've got a second degree polynomial parabola, once you tack on that fourth degree, it's still going to be somewhat parabolic, but what you've got is an extra little hill in there. If you did x to the sixth, it's still the same thing. It's still somewhat parabolic, but you're going to have an extra hill. If you did x to the 8th, you got an extra hill. X to the 10th, you got an extra hill. So it's just any time you tack that extra on, then you've got one more hill, which, yeah, that's right. Because of transformations, we always know going from x squared to a negative x squared, it flips your parabola upside down. It does the same thing for any graph. So to make a long story short, x to the second power parabola. As soon as you notice that your a value, that number out front, is negative, it's an upside down parabola. X to the fourth, a parabola with a hill in the middle. As soon as you notice that your a, your number out front, is a negative, it flips it upside down. Okay, so that's basic shapes of your graphs. Odd degree graphs. X to the first power, and these are just polynomial functions. We're not dealing with rational or anything. Odd degree graphs. X to the first power, you've got a line. If you notice in this case it's slope, if you notice the number out front is a negative, then it's going to be a line that slants downhill. Okay, from left to right it's going uphill, from left to right it's going downhill. X to the third power goes up, down, up. Negative x to the third power is going to flip it upside down. Instead of going up, down, up, it'll go down, up, down. X to the fifth power follows the same suit. Any x to the fifth power graph, you're going up, down, up, down, up. Just every time you add that extra exponent on, it adds another digit. That makes sense. And then negative x to the fifth power would be down, up, down, up, down. Go follow that. So in conclusion, if you have an odd function, you have an odd degree, I should say. If the numbers out front is positive, that's what this is saying, then your function is going to go, well, to the left it's going down, to the right it's going up. So from left to right it would be like up, down, up, down, up, down, up. If you make that number out front negative, it simply takes this and flips it over. If it's an even, like x squared, x to the fourth, x to the sixth, to the left you're traveling up, to the right you're traveling up. If you make the number out front negative, it flips it over. Okay. So, x to the third. here's what you need to get used to. It's going to be something like this. Anytime you got an x to the third graph, it's think about x to the first. It follows the same suit. To the left, as you travel to the left, you're going down. As you travel to the right, you're going up. Because think about y equals x. Determine the end behavior as, and I guess we need to explain this. All this means is x is approaching infinity. That means that your x value is getting bigger and bigger and bigger. What happens to your graph as your x gets bigger and bigger and bigger? And here's the actual graph I've got here. As x, start at 0, as x gets larger and larger and larger, what does y do? What does your graph do? Does it go up or does it go down? It goes up, right? So here's how you'd write it. As x approaches infinity, y approaches positive infinity. It goes up. Now let's talk about the other direction. As x approaches negative infinity, that's going this direction. As x gets smaller and smaller and smaller, notice your graph goes down. Your y value gets smaller and smaller and smaller. So as x approaches negative infinity, y approaches negative infinity. It goes down as well. That's pretty much a shortcut way of saying as x goes up, y goes up. As x goes down, y goes down. That's all you're saying in those terms. Okay. Negative x to the third. If x to the third is up, down, up, that negative out front is going to flip it and it's going to look something like that. And you see that's very similar to the graph. I didn't want to get it exact because I didn't want to scare you. So as x gets bigger, on this one, as x approaches positive infinity, what's your y do? Anybody? As x gets bigger, as you travel to the right, where does your graph go? Down. So as x approaches infinity, y approaches negative infinity. On the other side, Michaela, what happens as x gets smaller? As x approaches negative infinity, where's your graph go, Michaela? As you're going this way, does your graph go up or down? Up. Positive. That makes sense. X to the fourth. Think about x squared. To think about what an even graph does, think about x squared. X squared is a parabola. X to the fourth is a parabola with a hump in the middle. And you see here, it's a W. The reason this one is W, notice it's an even function. It's going to have symmetry. It's going to have that reflection of symmetry there. So let's go through these. Mary, as x approaches positive infinity, look at your graph there. As x gets bigger, what does your y do? It gets bigger. It also approaches positive infinity. As x goes to negative infinity, Viraj, what does your y do? As you travel to the left, where does your graph go? It goes up, right? So on this one, as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches also positive infinity. Will that always be the case for even functions with positive numbers out front? Yes. Okay. Last one, I think. Yeah. Notice this one is this one's not an even function. You got that extra x thrown in there that kind of warps it. So a mutated x to the fourth graph. The reason it's upside down is because of the negative out front. The reason it's that M shape, the reason it has a somewhat parabolic shape, and you see it's kind of parabolic, except for the hump in the middle. The reason it has that is because it's even. Its highest power is even. So negative x to the fourth, and you see here, as x gets bigger, y gets smaller. It goes down. As x gets smaller, y gets smaller as well. It's going down on both sides. We're not concerned with this middle. We're not concerned with what's happening in the middle. We're concerned with, this is called end behavior. End behavior is what's it doing way out here and way over here. way to the right and way to the left, and pretty much it goes down. That's what the arrows mean. To the right and to the left, it goes down. Okay. Sketch the graph of each polynomial function. Here we have y equals x to the third minus 5x squared plus 7x minus 3. Now, one thing on that previous slide that I kind of skipped through, one thing it did tell me was it's a smart idea for checker symmetry. If you have an even or an odd function, the reason that's a good idea is because you only have to graph half the function in. If it's an even function, I would graph everything over here and then just copy it to this side. If it's an odd function, I would graph everything on this side and then spin it and graph it. Like if it's up here, I'd spin it around and do the same thing down here. If it was here, I'd spin it around and do the same thing over here. Okay, if it was an odd function. This one is new. Okay. What I would like for you to do next, as we're graphing these, let's go ahead and find the zeros. Because that's going to tell me the 3 spots where it crosses is 3 points on my graph. So the zeros here, it's not, we can't factor by grouping. You can try it. Let's try to find some place where it crosses. Let's try 3. And the reason you can make a list here. Possible rational roots are all the factors of 3 over all the factors of 1, which is a very short list. 3 and 1 over 1, which is pretty much positive, negative 1, positive, negative 3. That's your short list of possible rational roots. I've got 1, negative 5, 7, negative 3. Bring it down, multiply, negative 2, negative 6, 1, 3, 0. So 3, 0 is a point on your graph. It is an x-intercept. And not only that, but now we can take this, which is x squared minus 2x plus 1. I can factor that and find my other 2. What does that factor into? X minus 1 times x minus 1. X minus 1 squared. So my 3 zeros are 3, 1, and 1. Since 1 is a 0 twice, I know my graph's going to touch that. Okay, it's not going to cross, it's going to touch. And I know that at 3, since it's a root once, it's actually going to cross. Now let's find some other points. And I know graphing calculators would be much easier here, but we're going to try to graph them by hand. We're going to take a trip back to the 70s. Plug in some more points. I'd probably plug in 2. And you've got 2 options now of how to plug this in. You can actually go in and do 2 to the third minus 5 times 4 plus 7 times 2 minus 3. Or if you want to, if you prefer, use synthetic division. If you're pretty fast at it, when you plug in 2, you get negative 1. You can always use synthetic division to plug numbers in. Let's plug in 0. That's pretty easy. Somebody plug in 0 for me. Should get negative 3. 1, 2, 3. We can plug in, let's just do one or 2 more. Plug in 4. And I'm going to do it synthetic division again. I'm just a little bit faster at synthetic. When I plug in 4, I get 9. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. And does everybody understand it would be pointless plugging 5? Because we know that this graph is not going to turn anymore. Because if this graph turned anymore, more than likely it's crossing that x-axis again. It's not going to. So my graph touches here, crosses here. So it's going to go up. It's going to touch. It's touching there. It's crossing. That's the graph of my polynomial function. And you can see, here's where I actually graphed it with a graphing calculator. Or, well, no, I flipped that picture. Same graph. Any questions? Next up, students will solve polynomial inequalities. We've been solving polynomial equations. Where is this polynomial equal to 0? Now we're going to solve, and we've done this. Been there, done that. We're going to solve where's this polynomial above 0? Where's this polynomial below 0? Okay, pretty easy. First one, x to the 4th plus x to the 3rd minus 15x squared plus minus 3x plus 36 is less than 0. Well, first step, let's find out where it's equal to 0. And then let's go from there and find out where it's below 0. I highly recommend graphing as a start. Here's your TI graph that corresponds with that. And I see there that it does cross at -4. And it looks like it might cross at 1, 2, +3. So keep those in mind, -4, +3. So graph it on your graphing calculator. That way you can find the zeros a lot easier. Let's check -4. 1, 1, -15, -3, 36. Y'all have not worked me any x to the 4th. Bring it down, multiply, add, multiply, add, multiply, add, multiply. Wow, we were right. 0. And again, guys, what you just did, you broke down x to the 4th into x minus 4 and x to the 3rd stuff. So if you want to write that back out, your equation or your inequality is now x plus 4 times this stuff, but don't even worry with that. Because take what you've broken it down into now and try to break this down again. And what did I say the other possibility was? 3. Let's try 3 and see if that breaks this down. 1, 3, which, hang on a second. Look at these. Would that factor by grouping? Do you see the possibilities there? It would. Let's do that instead. That 3 would work, but I want to, just to work on practice and factoring by grouping, we broke this down into x plus 4 times x to the 3rd minus 3x squared minus 3x plus 9. Group and group. And I just noticed when I pull a -3 out of this, do I not get this as well? All I can pull out of the first two, and I'm going to do brackets here. All I can pull out of the first two is x squared, and I'm left with x minus 3. What can I pull out of the second two? And always pull that negative out with it. -3, and you're also left with x minus 3. So that does factor by grouping. In my two terms now, I have x minus 3 in common. So I have x plus 4 times. Pull the x minus 3 out of both of those, and you're left with, anybody? Yeah, pull that out, you're left with x squared minus 3, and that is less than 0. And you see, you're about to see where graphing calculators come in so handy with these types of equations. Because if you didn't have this graphing calculator, well, let's do it without first, then we'll show you how much easier it is with that. I know that, here's my x-axis. I know that at -4, +3, and this would be, the solution to that would be plus and minus the square root of 3, which is about positive and negative. Somebody type in, I think it's 1.6. Type in root 3 for me, please, so I know where to put this. 1.7. So at -1.7 and at, let me erase that and put positive 1.7 there. Oops. There's my 4 crossing points. And notice I did say crossing points. Because it's important for you to know, is it going to cross there or is it going to touch there? Because we're looking for, where is my graph above and where is my graph below? Let's go back to what we just learned too. Positive x to the 4th. Y'all remember what positive x to the 4th looks like? It's very similar to a parabola with a hump. It's going to look something like that. So do you see how that relates to this? Your graph is going to come down, it's going to go up, it's going to come back down, it's going to go back up. And that's the 4 places where it's going to cross. So where will my graph be below 0? Again, think about what I just told you. An x to the 4th graph comes down, and then it's going to go below 0, right? So it's going to be below 0 from here to here. So it comes down, goes back up, it crosses it, it comes back down, and it goes back below 0. And then it comes back up, and then it stays above 0 forever. There's your solution. So we're teaching you all this and putting it all together for this reason. If you know the basic shape, if you know the exponent, or excuse me, the constant out front is positive, using that basic shape and knowing the fact that it doesn't just touch it, it crosses everywhere. Now, if it just touched it, then you've got a different issue. If it just touched this first one, then it's not going to cross, it's going to stay above. But since it does cross, you've got this type of shape, and it's going to be below from here to here. So your answer, it's below everywhere from -4 to -1.7. Or if you would like for that to be more exact now, you can go back and put in -√3. Union √3 to +3. Any questions? X to the 4th minus 4x squared. The first thing that I notice here, even function. Even function. And think about what that does to your roots too. If 3 is a root, -3 is a root. It's even, it's symmetrical. If 10 is a root, -10 is a root. If the square root of 3 is a root, the negative square root of 3 is a root. So here we go. First off, let's find the roots. We know what that looks like. Looks like that. It's an even function. And we need to know where it crosses. It crosses where it's equal to 0. Let's factor out x squared, and we're left with x squared minus 4. So our roots are what? 0 twice, right? And I'm gonna put in parentheses times 2. 0 is a root twice, and what else are roots? So my graph, and there's a reason I didn't put my x-axis there. My graph actually looks like this, to where it's actually touches. Notice that 0 is a root twice. It's not going to cross. It's going to touch there. So, and here's -2, and here's +2. So where are we below 0? Everywhere from -2 to positive. It looks like, and you're really close, but there's one problem. It does not include 0. So everywhere from -2, and if it included 0, if it was less than or equal to, I could say everywhere from here to here. But the problem is, everywhere from here up to here, it is below, but here it's actually equal to 0. So we're going to have to say everywhere from -2 to 0, it's below it, and everywhere from 0 to +2, it's below it. So that pretty much says everywhere from -2 to 2, except for 0. Today.